Given the following ODE, which is a mass spring dampener system, we want to use Laplace transformations to solve it. Now, for this problem, we are going to let the control be equal to 0. So essentially, u of t is going to be equal to 0. Now, in addition to the definition of the ODE, I also defined some constants. So for our dampening constant divided by our mass, it's going to be equal to 3. And for our spring constant divided by our mass, that's going to be equal to 2. So these are going to come in handy later. Now, before we start getting into the Laplace transform for our ODE, what we should probably do is write out some of the important Laplace transformations that we're going to use. So we can start out with the Laplace transform of our time-dependent x. Now, that is going to be equal to our frequency-dependent capital X of s. And then for our Laplace transform of x dot of t, that is going to be equal to s times capital X of s minus our initial position condition. And then if we were to take the Laplace transform of x double dot of t, that would be equal to s squared times capital X of s minus s times our initial position condition minus our initial velocity condition. Now there's actually one more that we're going to need, and that's going to be for the exponential. So we can say if we have the Laplace transform of some constant capital A times e to the a times t, where a is some constant as well, that is going to be equal to a divided by s minus a. So all of these are going to come in handy throughout the example. So with that being said, let's dive in. So if we take the Laplace transform of our ODE, so we'll have m x double dot plus b times x dot plus k times x is equal to 0. And what we can actually do is we can pull out the constants and then take the Laplace transform individually for x double dot, x dot, and x. So we can write m Laplace transform x double dot plus b times the Laplace transform of x dot plus k times the Laplace transform of x is going to be equal to 0. And again, the only reason we could do that is because m, b, k, and 0 are all constants. So now, after we did that, we can essentially write out our Lagrangian form using our three, or not identities, but essentially our derivations from before. So now we can write out, we'll essentially have mass times s squared times capital X of s minus s times x naught minus v naught. And then we'll have plus b times s times capital X of s minus x naught. And then we'll have plus k times capital X of s is equal to 0. Now the next step that we need to do is we need to pull out our capital X of s and essentially isolate it from the rest of the equation. So after doing that, we get that capital X of s is going to be equal to x naught times s plus b divided by m plus v naught divided by x naught, all divided by s squared plus b divided by m s plus k divided by m. Now, what we can do is we can use our constants that we defined above. So where we have b divided by m is 3, k divided by m is 2, and we can plug those in. So then we will get x naught all times s plus 3 plus v naught divided by x naught, all divided by s squared plus 3s plus 2. Now there's one more substitution that we should probably make just to make it look a little bit nicer and simpler to work with as we go, is we can define chi as v naught divided by x naught, which then will leave us with capital X of s, which is going to be equal to x naught times s plus 3 plus chi, all divided by, and we can factor out our s squared plus 3s plus 2 as s plus 2 times s plus 1. Now the next thing that we can do is we can try to split up our denominator by doing factorization by parts. So we can say k1 divided by s plus 2 plus k2 divided by s plus 1. Because what we want to do, notice that we have some constant in our numerator, and then we have s and then some constant, which looks awfully familiar to this Laplace transform relation that we defined earlier for the exponent. Because essentially we're trying to set up our equation to solve for whatever this a is, so we can take the inverse Laplace transform to get back into the time domain. And then we basically solved our entire ODE just like that. So what we can do is we can start to solve for k1 and k2. So for k1, the way we will calculate that is we'll take the essentially the root that k1 is above, and this will be s plus 2, and we'll multiply by x of s, and then evaluate at that root. So when s is equal to -2. So let me say that again. So the way we solve for k1 is we take the root that it is above and we multiply by the entire capital X of s. And then we evaluate that at that root. So when that root is at 0, which in this case for k1, that will be when s is equal to -2. So we can start to write that out, and we get x naught s plus 3 plus chi divided by s plus 1. And we're going to evaluate this at s is equal to -2. Now here in the denominator, we're going to have s plus 1, or -2 plus 1, so -1. So we'll have negative x naught times our s, which would be -2 plus 3, or essentially 1 plus chi, just like that. And now we have our first k value. So now for k2, we'll essentially do the same thing. So we'll take our denominator, which would be s plus 1, and we'll multiply by capital X of s and evaluate at that root. So when s is equal to -1. So then we'll have x plus 2, x naught, and then we'll have s plus 3 plus chi, and we'll evaluate this at s is equal to -1. So in our denominator, we'll have -1 plus 2, or 1. So then we'll have x naught, and then s will be -1, so we'll have -1 plus 3, which will leave us with 2, and then plus chi. So now all we have to do is plug this back into x of s. So we can say x of s is going to be equal to, and then, it's going to be equal to, so our k1 value is going to be negative, so I'll do k2 first. So we'll have x naught, and then 2 plus chi over s plus 1, and then minus our x naught, and then 1 plus chi divided by s plus 2. So now we're in the home stretch. All we have to do is take the inverse Laplace transformation to get our capital X of s in the frequency domain and transfer that back to lowercase x of t in the time domain. So we are almost there. So hang in with me. Hang in there. So we can write out, if we have lowercase x of t, that is going to be equal to the inverse Laplace transform of capital X of s, which is going to be the inverse Laplace transform of x naught 2 plus chi divided by s plus 1 minus x naught, and then times 1 plus chi divided by s plus 2. Now you could split this up. Actually, yeah, let's split this up. There we go. So we'll do the inverse Laplace of essentially this right here. And then same thing. So we'll do minus inverse Laplace of same thing right here. So then from here, what we get, so we have our exponential, right? So before we said we had some constant, capital A, times e to the lowercase a times t. That's going to be equal to capital A divided by s minus a. So here we will get that we have essentially our constant a here. It's going to be our x naught times 2 plus chi. And then we're going to multiply by e to the essentially our a, right? Or e to the a times t, where a is the negative of this value, that 1 there. So I have e to the 1 times t. And then for the other one, so we'll have negative x naught 1 plus chi, and we'll have e to the negative of that value, which will be negative 2 times t. So we can simplify this just a little bit more. So we can say x of t is going to be equal to x naught, and we'll have 2 plus, and then we'll substitute our chi back in. Where our chi, remember from before here, it was v naught divided by x naught, v naught divided by x naught times e to the negative t minus, oh, we pulled out our x naught, minus 1 plus chi, which then we're going to substitute for v naught divided by x naught, e to the negative 2t. And we just solved an ODE using a Laplace transform.